Welcome to this week's lecture. We will talk about support vector machines today. And before we do so, I want to look at the perceptron algorithm as a very simplistic kind of support vector machine with some commonalities and some differences. So when we look at the perceptron, sometimes that's also hailed as a predecessor to neural networks. Then we have data based on which we do the training, right? And we indicate that a data point belongs to a certain class, as we do here, either -1 or +1. And we want to learn a classifier. And the idea is that our function f hat returns for a data point a value larger than 0 if the class is positive, and smaller than 0 if the class is negative. And we have a correct classification when the product of f hat of xi times the classification, the true classification, is larger than 0. So every time we violate this constraint, we have a certain loss. And when we have linearly separable data, then we can introduce such a vertical bar to separate the one class from the other class. Here is a very large difference between these classes. Here we have instances that are closer to each other. Of course, we not always have linearly separable data points, examples, right? Here would be an example where there is one data point which is a kind of an outlier. Or here we have an organization of data point such that no straight line will do in order to separate the blue class from the red triangles. Of course, what we can still do is we can map our given data points into a feature space that would perhaps allow for the separability of the two kind of classes. So we can now write, if we have such a linear separability, right, with the prediction for the blue class being below 0 and the prediction for the red class being above 0, we can then describe this function by a very simple linear function, namely W transpose x plus b is the value where, well, W and x are vectors and b is a scalar. And when we do this, well, here we have this corresponding nice description. Then the discriminant is such a line, and this line is exactly where the value f hat of x equals 0. So not assigning the points on this line are not assigned either to the positive or to the negative class. And the W is actually exactly the normal vector to this line. So normal vector, just so you remember, when we have such a line, the normal vector is perpendicular to this discrimination line. And the B is a bias which describes the distance to the origin. So if we have such a coordinate system, we have such a line, we have such a kind of a normal vector, then we have a certain bias here, which is just the distance from the origin of this coordinate system. W is known as the weight vector. And, well, we have then a nice, very simple linear description of our classification model. Now, can we learn this when we, and by the way, of course, in this very simple example, we can also write our xi as we did with linear regression with 1, xi1, etc. And then, of course, this boils down to a specific weight vector that includes some bias too here. So when we have a linear line as a separation between these two classes in a 2D case. Then in a 3D case, we have a discriminant which is a plane, such as indicated here. And in n-dimensional space, the discriminant is a hyperplane. And all of these times, we describe this hyperplane or this plane with the normal vector plus the offset from the origin. So the formulation doesn't really change even if we have some higher order description. And to classify new data, all that we need is this W, which includes this bias term. Yeah? Why is it formulated? What exactly? Because what we want to get out here is a scalar. X is a vector, and we want to have the dot product. So a vector dot product, the other vector, which is naturally the case if we have a row vector times a column vector. And so the perceptron classifier, with such training data, we try to find the appropriate weight vector. We start with a weight vector, for example, to be 0, or maybe for practical reasons it's often good to initialize the initial weight vector with some small perturbation around 0. Shouldn't matter here much, but in general that's often a good thing to not exactly have zeros all over the place. And what we want to do is we want to fulfill this condition that if we have a violation of our model, and the violation happens exactly when our model for a point times the correct label is less than 0, in such a case, we change the weight vector, namely we take the weight vector that we have so far, and then we take this data point times the sign of our prediction function, and this sign is the wrong one, and therefore we negate it. And then we also have a learning rate alpha, and we basically change this wrong sign by subtraction a little bit in the direction in order to get the right kind of sign for this particular data point. Well, for 0, of course, well, we have to think about what to do. And so here is a small example. If we have here these data points, here is the one which is on the wrong side. Here we have our initial vector W, and what happens then is we have to subtract from this vector, and this subtraction moves this line in order to put this data point, which is under investigation, onto the right side of the line. Maybe this doesn't happen in one step, maybe we would need several steps. So that depends on the alpha, how large this alpha is. It shouldn't be too large because otherwise we might oscillate violently between different versions of putting this on the wrong line. But of course you see that with changing this, there may be other data points end up on the wrong side of the line that before were on the right side of the line. And when we converge, then our W is nothing else than a combination of these individual data points, a linear combination of these different data points. This is something we will use actually also later. So the whole W is influenced by our data points. Now, here is a little bit more elaborate example of how such a good line could look like. This line separates these blue crosses from the red triangles. And every example is on the correct side of the line. But what is maybe not so good with this example? Why? What could be a reason that we don't want to stop here? Right. So I just try to repeat what you said. These crosses are super close to this discriminatory line. And why is this a problem? Right. So I have not understood all the sentences, but some stuff that I understood I found correct. So just imagine, like, here's this blue cross, and now just adjacent to this blue cross, just on the other side of that line, you would classify to belong to the class of red circles. So intuitively speaking, that's not what we want, because something like, let's say, in this place is more plausibly a blue cross rather than a red circle, right? So we're not happy with this kind of classification, even though our perceptron learning would stop here. Okay? So we converge here. Well, conversion is also not very fast, but what is even more disturbing is that the separating line is just very close to the training data of one of the classes here. And this is an observation that has led to the development of the support vectors. So what is the best W? And the idea is, if you look at these different examples, well, this is clearly a wrong vector, right? Because it doesn't separate the two classes. This is a correct vector, but here this point is very close to this line. And this is a very good separating line, because this separating line is far away from all of the examples. So being far away from all of the examples of the positive and negative classes, this is something which is intuitively good, because even if these examples wiggle around a little bit, which they always do because they are always samples from an underlying distribution, then we would still come up with the same, or at least a very similar result. While if we start wiggling here with this model, we may end up with classifications on the wrong side of the discriminant line, or discriminant hyperplane. So this brings us to this core idea of the support vectors. If we have a discriminant line here, now we distinguish again the bias from this other part of W. You will see in a minute why. And what we want to have is that the support vectors are as far away from this line as possible. Now, what are support vectors? Support vectors are just these vectors here and here and here and here that are closest to this discriminating line. And in this example, it's exactly 4 support vectors. It need not be the case. It could also be that, let's say, this point would just be here, and then we would just have 3 support vectors, for example, in this case, right? So the support vectors are those that have the closest distance to a discriminant line. And then the idea is that here we have some distances as indicated by this blue line or blue dashed line or this red dashed line, and the margins between should be as large as possible. Now, when we look at this discriminating line, that's exactly where our model W transposed x plus b equals 0. So where our model doesn't say that's positive or negative. When we now look at this distance, actually the exact distance of this line here is b divided by the length of W. So if the length of W is exactly 1, then of course this is exactly b. And then we have the support vectors that are closest. And this closest should also be closest as measured along the vector perpendicular from this line. Because, right, if you think what is the distance of this support vector to this line, it's of course following a course perpendicular to this discriminant line. So what we want is that these margins are as large as they can get. Now let us first describe all the distances between points here and the line. What is the distance between point xi and this hyperplane, h? And the distance is nothing else than the class times w transpose xi plus b divided by the length of this perpendicular vector. The length of this perpendicular vector doesn't really play a role, right? Because all the function of this perpendicular vector is to indicate the direction. So we can choose whether we want to have a perpendicular vector which has unit length 1 or some other length. So, but this then eventually gives us the distance when we divide by the length of this w in this Euclidean space. Yeah? Okay, so this is now our distance formula, how far the points are away. And of course, if the distance is positive, then the point is on the right side. And if it's negative, then the point is on the wrong side of this plane. Yeah, and I just mentioned that it doesn't matter how long w is. But of course, we can take a w such that exactly our support vectors, the ones that are closest to the line, they make this formula become exactly 1. This is just something we can choose, and it becomes convenient if we do this. Well, we could do it differently, but that's just a convenient choice. Note, when we try to maximize these margins, how is the comparison of this support vector to the line and that support vector to that line? That, of course, should be the same distance, right? We want to be as far away from the red class as from the blue class. Therefore, the support vectors have all the same distance from this hyperplane. The ones that are further away, they're not support vectors. Okay, so what do we have now? If this formula is exactly 1 for the support vectors, then the distance indicated here is exactly 1 divided by w. Right? You just have to look at what is the projection on this plane, what's the distance between the two, then the bias doesn't matter, and then it's exactly 1 divided by w, which is this distance, the absolute value of w, of course, which is exactly this distance of the support vectors from this hyperplane. And remember, this distance should be as large as possible. So, what we want to do is we want to maximize this term for our support vectors. Instead of maximizing a term, we could, of course, also minimize the inverse, right? That's, of course, also often done. So when we look at 2 times this margin, this is 2 divided by the absolute value of this vector. Here we have the formula is 0. Here we have this formula is +1. Here we have this formula is -1 for such case of linearly separable data. Now, we maximize this term, but what we require is that this term, the correct class, times the value, the prediction for all the data points are larger or equal to 1. Remember, for the support vectors, it should be exactly 1. For all the others, this term must be larger than 1. And so we have a maximization problem subject to constraints. So this is something that we didn't have in this lecture until now, but which is a very frequent theme that we try to optimize something given some constraints. Now, instead of doing the maximization, we can also do the minimization under the same constraints, and instead of minimizing w, the absolute, we can also minimize w square. I mean, that's something we had before also for linear regression. So this is a quadratic optimization problem now with linear constraints on what are valid areas for our W's. Remember, I mean, always have to look what is given. The xi's and the yi's are given. These are part of the training data. What we have to find is the w's and the b. And of course, if we find the w, then the b becomes quite obvious. Now, this is just a side note here. This is a different problem than the problem that we had when we tried to do linear or logistic regression. When we apply linear or logistic regression, we also find a separating hyperplane. However, when we do linear or logistic regressions, all the data points in our data set play a role for determining this hyperplane. Now, when we do the same or similar problem for support vector machines, then what is important for this plane are only the support vectors. All these points which are further away, they don't play a role in positioning this hyperplane. Because all that matters is that their product is larger than 1. Right? W transpose xi plus b, parenthesis, times yi must be larger than 1. That's all that we care about, but we don't care about otherwise how far they are really away from the hyperplane. The only thing that we care is that the support vectors are a maximal distance away from the hyperplane. And here, in linear regression, even these points here would influence the shape of this plane. Okay, so these are the general considerations. And we have not looked at how to solve the problem, but that will come. Let us also look at the problem that it becomes hard to do linear separation. Here we have a problem, and we can linearly separate the data, but what you see is that the discriminant line that we find is okay, but it's not great because these data points here are very close to this line. So we have a discriminant, but the discriminant is not very good. It will be not very robust. And maybe, and it is quite likely, that this data point is just an outlier, and it would be best not to consider it. So here in such a case, such a large margin solution that puts this even on the wrong side could be a better solution in order to maximize accuracy, especially given that we also have always the base error, right? So there's a trade-off between how large the margin can be and the number of mistakes we do on the training data. So in this case here, we have a larger margin if we ignore this data point, but we do a mistake here. Here we have a very small margin, a very small offset to support vectors, but no mistake with our training data. Now, what do we prefer? Actually, for this toy example, this one would be the more promising one to come up with a better solution in the long run, where we generalize better on our test data in the future. Now, how can we formulate this problem? Well, the idea is that we do not only have support vectors, but we also have points that violate the margin. So this point here is too close to this discriminant line. And what we say here is that we introduce some slack variables. So 1 divided by the length of W was the distance to the support vectors. And here we have a data point which is just zeta I divided by the length of W away from this discriminant hyperplane. So what we allow for is that such kind of distance is less than the distance that we want. We have a misclassified point.
Or we have even a point here which is entirely wrong, and this has a very large slack compared to this original support vector target. So the idea is to introduce these slack variables zeta I, that if they are between 0 and 1, the point is between the margin and the correct side of the hyperplane. So we have a margin violation, but we are still correctly classify these points. And if then this slack is larger than 1, the point is misclassified. So we have some distance away here and a larger distance away here. So you see that in this case, actually, the zeta I is more than this margin. So this is a 1 divided by W, and this is another 1 divided by W. So this zeta I is more than 2 divided by W away from this targeted line. So now what we want to achieve to do this trade-off between maximum margin and misclassification, we still have the same objective of minimizing the size of this vector W squared under this condition, but we allow that the constraint is not just larger than 1, but it's larger than 1 minus the slack variable. Remember, between 0 and 1 for this slack variable, we have a margin violation, but classify correctly. And if this zeta I was larger than 1, then this is misclassified, because we would only require that this whole thing is larger than, for example, 1 minus 2, larger than minus 1, and minus 1 is a wrong result. So when the zeta I is larger than 0, then we have some unintended consequences. And rather than preventing these unintended consequences, we say we allow them, but we punish them. And so our loss here is now not only the minimum of W squared, but we sum up all these violations, zeta I, connected with some regularization parameter. So every time we violate the constraints, we say, but you may violate it, but we punish you for this with our loss function. So this is now an optimization problem subject to some constraints. And now this C describes how easily we can ignore these constraints. If the C is very small, then we can easily ignore the constraints and get very large margins, but maybe with many points on the wrong side, or at least with some margin violation. If the C is infinite, then this means all constraints are enforced and we get a hard margin, if this is possible at all. You saw some examples before where this was not possible at all, when some outliers were on the wrong side, amidst other examples. And, well, in between we have large C's that make constraints hard to ignore, but maybe lead to some narrow margin. What we have all the time is a quadratic optimization problem with unique minimum. Why is it unique? Well, it's convex. This is a convex problem. It's a parabolic function, and this is a linear function. So given a certain area that we allow, this is a convex optimization target within a certain area. That comes with the optimization. So at this point, we have not really said what are the support vectors, right? And the support vectors are implicit exactly by this constraint. And yeah, if you don't have this part, if you don't have the slack variables, then the support vectors are those that make this exactly become 1. But you are completely right. So we say, assume we have support vector, then this must be fulfilled, but we don't even say which ones are the support vectors. But this, even no matter which support vectors we have, the whole optimization and constraint fulfilling applies. So this is quite a trick, to say I don't know it, but this applies, and then actually if I maximize it, then I get my support vectors. And that's a quite clever scheme. Okay, so that's now our constraints. Now, of course, what we require here are that the zeta i's are larger than 0, right? Because otherwise, what would happen if the zeta i's could also be negative? Then this punishment wouldn't work anymore. We would add to the punishment, but we would also subtract from the punishment, and that, we would lose what we actually intended to do. So that's not possible here. We cannot subtract from the punishment. So this is a constraint that we are, all the points are beyond the support vectors other than the ones that violate this, but this violation gets punished. Now, how can we write this in one formula? Well, we can, of course, resolve this for zeta I. So here we could say zeta I is less than, and we can bring the 1 on the other side. But then we would have minus zeta I, so we can multiply with minus 1 and then switch around the inequality sign. So zeta I becomes larger than this term minus 1 minus this term, which is exactly what we have here. So then zeta I is the maximum between 0, it cannot be smaller than 0, and 1 minus this term yi times what our model gives us. And that means that now we have this unconstrained optimization problem, which is we look for the minimum of this weight vector squared plus, then we have here this punishment term. Note that we had before this c at this place, but we can divide by this c and have this c instead here in the denominator. That doesn't change anything really. And we have the sum of this kind of punishment. And this is now our nice formula. And now what we get is we have basically here our regularization. And here we have our loss function. So we have sort of like flipped around how we started. What we want to achieve is that we are on the right side of our function by this kind of loss. Remember, this here, this term indicates that our classification is correct. And if this term is larger than 1, then we have a loss of 0. Because if this is larger than 1, then we have 1 minus 2, for example. That's minus 1. But minus 1 and the maximum of 0 is 0. So that would be a loss of 0. On the other hand, if we have here, let's say this is 0.5, so positive but not far away from our discriminant hyperplane. If this is 0.5, then we have 1 minus 0.5 is 0.5. The maximum of 0 and 0.5 is 0.5. So we have a little bit of loss because we're not far away from our discriminant hyperplane. If this is the wrong side, then this is, for example, minus 1. Then we have 1 minus minus 1 is 2. Maximum of 0 and 2 is 2. So now we have a significant loss. And do I have a picture? And the loss that I have here is like this picture. So here on the right, I have the correct class times my prediction. And when my prediction is above 1, then the loss is 0. And if the prediction is below 1, then it increases like this. This is the hinge loss. That's just the name for it. And it's nice because it tries to push away from this discriminant line. In this area, even though we are doing the right prediction, it pushes away from this discriminant line. And here, clearly, we are on the wrong side of the prediction. And the hint, the 0,1 loss is indicated in blue here. So when the blue line is 0, when we don't do a mistake, but we don't have a good classifier yet. But of course here we do a mistake, but the further a point is on the wrong side of the line, the larger the loss. That's what we want in order to push our discriminant line to put our example points on the right side of the discrimination. So the support vector machine uses this hinge loss implicitly. And you can see that this red line, in a way, sort of approximates the 0,1 loss. But it does a bit more. It pushes this discriminant line. Okay, so that's neat. So this is now our loss function. And we say this is the loss because this is where our model goes wrong. But in addition to this loss, what we want to achieve is that this W square is supposed to be rather small. Remember what we did with linear regression and ridge regression? We had a different loss function there, but this almost looks like ridge regression, where we had our beta square. We wanted to have small parameters, and we squared them for ridge. So you see, there is actually a regularization which is similar between linear regression or logistic regression, where we can also do ridge regularization, and the support vector machine, where we also do some sort of ridge-like regularization. It's a bit surprising, right, that we started quite differently and end up then with this kind of consideration. Okay, so now how can we produce? I only talked now about how we model support vector machines, right? And by the way, this is also a question that I would ask in an oral exam, yeah? So like, what is the model of how do you derive this kind of loss function in case of a hard margin and in case of the fact that you have some slack variables? And now, of course, since we have this loss function, what we can always do is we can always do gradient descent, just as we did for the perceptron. For the perceptron, we had some mistake, so we just changed our weight vector in order to make this mistake smaller, to reduce the loss. And so what is gradient descent in a more general way? I think I've mentioned it a few times, but I've not really explained it so far. Gradient descent or gradient ascent is when you have some complex function and you don't know exactly how this complex function looks like. And so I was once skiing on a glacier, and then there was some snowstorm coming up, yeah? And what happens when you are in such a snowstorm? It was not a violent one, but it was one where I could look around me only like for maybe 2 meters. Yeah? First you go very slowly, yeah? That's the one thing. And the other thing is, it's very hard to see where you get down to the to the restaurant, to the base, and to your car, right? So all that you can do is actually, you look around you and look, where is the steepest decline? That's probably where the hill goes down, where you probably get back. And of course, in addition to that, you look out for these kind of posts where you could leave the skiing slope, the official skiing slope, which is where you don't want to go because some cliff might come or something like that. Yeah. That would, of course, be the steepest descent possible, but that's not where you want to go. So, but it's very comparable. You just look around you in a small vicinity of a few meters, and you try to go downhill. And this is the problem that you actually also have here. When you have such a complex function that you don't know, you are at some point and you try to reach either the minimum, that's gradient descent, or the maximum, that would be gradient ascent. So gradient descent, if you have a loss and you want to minimize the loss, you do gradient descent to reduce the loss. So your hill is described by your loss function. The loss function is this beast here. And you try to, you can evaluate your loss function, and you can also evaluate it around you. You cannot look globally everywhere, right? And you try to look for the steepest descent to get to the safe valley as quickly as possible. That's where you have hopefully the best result for your function f hat. And rather than evaluating the vicinity around you, which is something you can do, what you can compute oftentimes is the gradient. The gradient of a function is nothing else than the vector that indicates to you where you can go down the fastest, or in the opposite direction, go up the fastest. So if you have such a function f with several directions, then this points to you to the quickest descent. So this picture here, by the way, shows these I'm not sure how they're called. With temperature, they would be called isotherms. Yeah, in a map, this would be the lines of equal height. And if these blue lines are the lines of equal evaluation of your function f. And the gradient is nothing else than the partial derivatives in all the different dimensions that you have, giving you a gradient vector which indicates to you how can you get down the fastest down the hill, or fastest up the hill. Fastest up the hill, and then if you subtract, it's down the hill. Okay? Of course, what you need at these points is a differentiable function. So you can compute the partial derivatives in all the different dimensions of your function. And so when you do this several times, like me going down this skiing slope, yeah, you get down to the valley. Sorry, I didn't understand. Is it always possible to compute a derivative? This is possible if you have a derivable function. Right? So when we look, let's look at this function here. Always? No. But we can solve it depending on how our loss function looks like. So this is our loss function here. Right? So now we can look at how our loss function looks like. So this is a squared function, so that's not a problem to derive. Yeah, w to the power 2. This is 2 times w. So this part we can derive. This part has some is non-derivable at the point where this term is exactly 0, because there is a discontinuity in the derivation. Not a discontinuity in the function itself, but a discontinuity in the derivation, which is exactly this point here. Here, at this point, there is no derivation. On the other hand, practically speaking, you have to hit exactly this point this is a bit like throwing or pulling a random number from the real line and hitting exactly this point. And even if you do so, you could say, okay, there's no real derivative here, but let's just take the number 0 or whatever. Yeah, it doesn't really matter that much. Yeah, because when you draw a number randomly from the real line, the probability of hitting exactly this point is basically 0. And if it happens, you could even just draw a number again. So so the theory gives you a little bit of problem. The practical experience, not really. Of course, if you have a function here which would be where you would hit such a non-derivable point all the time, then you would have a problem. Okay, so here we don't have this problem practically speaking, and so we can just go down this valley or sometimes climb up the hill, depending what we want, in order to hopefully reach this point. This is, for this simple mountain or simple valley, very simple, there can be problems, and there are problems with gradient descent. For example, here we have such a kind of saddle. Now, you start, for example, here, you go up, let's say you go up, I mean, going up, going down, it's always just multiply with -1 and you get the counterpart, right? So here we want to go up to reach the highest point in our picture. That means we go up, and here we go up, 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 and we end up maybe somewhere here. However, the largest point in this picture is here, or maybe here. So what does this mean? We get stuck in a local optimum, and that can happen, right? And this can happen when you ski, because maybe you go down because you only look away for 2 meters. You could potentially end up in such a trough, where you then have to climb manually again out, which is not a nice experience. I mean, here the posts helped, so I didn't end up in such a trough. But actually here we don't have these posts, and so yes, you could end up in such a local optimum, in such a trough, and not find the global optimum. Now, here we are in a better situation. And why are we in a better situation? Because this loss function is convex. And because it's convex, it has a unique solution. So first, let's look about the general problem. Here we have such a hillside cut up in 1 dimension, but you see the same problems in 1 dimension as in many. If you are somewhere here, you walk to this local minimum and you get stuck. Because basically at this point, your gradient says don't move. You don't get any a better point. But of course, if you would be here, you would have a better global solution. But you don't know it. What do you practically do? Sometimes you restart your gradient descent. And there are several other approaches that I will look at in a later slide deck with neural networks. So the question is, when is our local minimum also a global minimum? And now, what is a convex function? A function is convex if it satisfies the fact that for any point, so given 2 points, here we have a point x0 and a point x1, and we evaluate the function f at x0 and at x1. If any point between x0 and x1, the function value is less than the average of these 2 values. Now, this is easier to understand when you look at this picture. So a convex function behaves basically like such a trough. And when you take this function value of x0 and this function value of x1, you basically say for any point in between, the value of the point in between is less than the direct line. And this does not only apply for these 2 points, x0 and x1, but for any pair of points that you pick. And that means for any pair of points that you pick, that the gradient gives you the right direction towards the local and global optimum. Right? You can imagine this if you have such a kind of function. If you're here, the gradient goes, go here, go here, go here. And even if you jump too far, the gradient will tell you to go back. So you can never get stuck. That's a different picture than here, because here you can get stuck. And this notion of convexity formulates this point that you cannot get stuck. How does this help us? Here first, some further convex functions. So a parabola-like structure, or even such a V-like structure, is convex. This is not convex. And how do we know this? Well, we could, for example, pick this point, x0, and this point, x1, we draw a straight line, and some of the points are higher than this straight line in between. So we would have a counterexample to the function being convex. And correspondingly, this is also the hill that gives us the problem in finding the global optimum. So, and if we have such convex functions and we add 2 convex functions, the resulting function is again convex, which is not a big surprise, because you can just take this definition and instead of f, use a convex function g and a convex function h, and then you define f to be g plus h. And obviously it must fulfill this criterion, because otherwise one of the 2 functions that you put in would not be convex. And now w squared, this is such a parabola, and this hinge loss is also a convex function. So if we add these 2 convex functions, we have a convex function, and therefore the gradient descent for our support vector machine gives us a global optimum. So this is good, right? So we can actually arrive at such a very nice solution. So the gradient descent algorithm for support vector machine is then simply, I have some weights, and the weights in the next round are given by simply subtracting the gradient. So I go here, the gradient of the loss, and as it depends on the w, and I have some learning rate eta. Quite often this learning rate is not constant, but I start maybe with large steps in the beginning and with smaller steps at the end. And we can rewrite the minimization problem. So if we define lambda to be 2c, then the minimization problem becomes 1 divided by n, where n are the number of data points, lambda divided by 2w squared plus this hinge loss. And the result will be the w transpose plus b. The subgradients for the hinge loss, so the loss derived in the direction of my vector w for this part of the function is minus yi xi. So here we are in the wrong part, so to say. And in this right part, the loss is just 0. So once we are here in this place, there's nothing to improve with my discriminant line, because this point is already further away, or at least as far away as the support vectors. And of course, the other subgradient will be this 2 times lambda w, yeah, if I derive this part. So overall then, the iterative update is the old weights minus the learning rate and then this gradient. The gradient consists of lambda wt, this is just this part derived, plus this other subgradient that we just looked into, which makes this, is based on this distinction. If this product is less than 1, then it's this, and otherwise it's simply this part. So this small distinction into where are we with regard to our discriminant line and our support vectors. And then typical learning rate might be that our eta of t is 1 divided by lambda t, so lambda a constant and t is just the time. So as time progresses, the learning rate gets smaller and smaller. Okay, so practically speaking, we can now already solve a linear discrimination problem for our support vector machines. However, we are right now limited to really a linear discrimination. Now, there is an analytical solution for the support vector machines, and the theory behind this analytical solution for our support vector machines also will give rise to a more powerful representation that goes beyond the linear system that we looked at right now. And therefore, let's now look at this theory. And this theory is not only relevant for the support vector machines, but this dual formulation is also plays a key role in modern machine learning. For example, there's one junior research group leader, Luis Jamon, here at SimTech, and he works or has elaborated a theory on learning with constraints. What kind of constraint? I mean, right now we learn with constraints, in order to do this separation, but you can think of further constraints. Constraint could be that two groups, males, females, are treated fairly, that there is no distinction between the two. Constraints could be that you want to have a certain safety requirement, or that your dynamical system behaves within certain boundaries, physical correctness, and things like that. And these are additional constraints you want to put into your machine learning system, such that you do not only learn from data, but that you also learn from additional knowledge that you have. So that's where you need learning from constraints. And you need it also here. And the underlying theory is also based on these dual representations, which comes from mathematics, right? I mean, machine learning didn't invent that. It was all made up in optimization and mathematics long before that by, I think, one solution is by Lagrange, so it's like 200 years old, way before machine learning. But it's used here. Okay, so we have our support vector machine as a linear classifier, again defined by W transpose X plus B. And this has led to the primal problem. And you have now seen these primal problems on several slides. So no surprise, primal problem being that you look for the minimum of this vector W in some d-dimensional space, W square, which is our regularization, plus our hinge loss. And now the dual problem is to get rid of the W for a different representation of f hat. And this different representation of f hat leads to a representation of our function that takes a weighting alpha I of the correct classification yi times the different data points that we have, or different support vectors that we have eventually, times the data point under consideration plus our b. So this is what we want to achieve given this optimization problem. And what we will see actually here, we represent this f in terms of all our data points. What we will see later is actually that only the support vectors play a role here in the very end. And what we will also see later on is that we multiply the x's with the support vectors. Well, the new x that we give, the new object that we give, we multiply with the support vectors. And this we can do in our original object space. This we can also do with the kernel trick that we already had with linear regression, logistic regression in a higher dimensional space, and where we also can then do nonlinear separations. You will see how that comes. I just tell this to tell you that it's worth paying attention. So we want to minimize this quadratic form with these constraints. That's what I showed you before. And well, at least one support vector will reach the 1, obviously. Usually more than 1. And so what we do is we have this loss function. And the loss function depends on the W and the B. And we can also include some alpha and say we punish every time that this term becomes positive. Now here actually we do this analysis for hard margins. There are generalizations, but we don't go into this at this point. You get the basic idea without the slack variables here. But it exists also for slack variables. So when the constraints fail, the objective function is punished. And so we want to maximize this function now under the constraints that this g of x is a. So here we have a kind of punishment. How do we do this? Now there exists this very old approach. I'm not sure whether Lagrange invented it already a long time ago or whether someone used some ideas on which they built this. I didn't inquire for that. So it's a very old problem to optimize a function, to maximize a function under the constraint that some second function, g of x, has some value. Now there is a solution for this general problem with so-called Lagrange multipliers. So rather than look in which area does my g of x has exactly this value, I optimize the function f of x minus lambda g of x minus a. Obviously, if g of x and a have the same value, then this whole thing is 0, then there is no punishment. And what I introduce here in order to make these constraints become relevant is some lambda, which is the so-called Lagrange multiplier. There is a, by the way, they don't show this here, there's a very nice visual explanation of Lagrange optimization at this point. So I recommend for you to look at this. So this is the Lagrangian. Now we can take the derivative of this Lagrangian with regard to x and set it to 0 because we want to find the optimum for this. And then when we have this optimum, this is a kind of an estimate for x. This x, of course, depends on the lambda. And this is a bit, we don't really know what this lambda should be. But no matter which lambda we plug in, we get some kind of optimum. So the x that we get is not really yet the optimum, but it's a better one than the one that we have right now. And so what we do is we plug our estimate of the x in the Lagrangian, take the derivative with regard to the lambda, and then look for the perfect lambda according to this x. And then we find some optimal value for the Lagrange multiplier lambda. And then we can repeat that. We can plug the Lagrange multiplier and estimate x newly. So when we have such a quadratic form with such constraints, etc., we include the hard constraints into our loss function. And now the alpha i's are our Lagrange multipliers. These are the ones that we look for. And the Lagrangian primal problem now is we look all the time for the minimum of our loss function, our w and our b. But what we want to have is a maximum for our alpha. So when is this constraint best fulfilled? It is best fulfilled when this alpha is a very large number. We said before, when the alpha is infinite, then we have a hard constraint. So what we want is we want to find the best, the largest alpha possible. And that's what we do here. We look for the maximum for a particular alpha, and then look for the minimum that we find here. And the alphas must always be larger than 0. So what we don't want is we don't want to provide awards, so to say. So we find the optimum using the derivatives. We also have to find the optimum for the b. So we look for the derivative of b of our function. The derivative of b is actually 0. And yeah, because we set this derivative to 0 to find the optimum. And the derivative then, if this is 0, that means we have here this term. There is no b in there. So therefore, we have the derivative of b is alpha I yi. And so the derivative is the sum over alpha I yi, and this we set to 0. So this is one result that we get from setting this to 0 to optimize the result. And then we also set the loss to 0 for all the derivatives, for our different partial derivatives of wj. So these are all the different components of our vector w. And all of them must be 0. And now if we take all these wj's, we basically have to look where do they play a role. And what we get when we do this with the above, then what we find is that the wj is just this combination of data points with regard to the jth component times the correct class times our weight alpha I. And if we generalize from each component wj to the whole w, well, all that we do is we get away from the component-wise consideration of x to all components of x or xi. So w is nothing else than a linear combination of Lagrange multiplier, correct class, and xi. So w that we get here is a linear combination of the data instances where we don't know the alphas yet. So our loss function, given that our w is this linear combination, is now this whole term, which we can take apart. The w square half is nothing else than this linear combination multiplied with itself. Then this loss function, we have the alpha I, the yi's are given. The W transpose xi are this W times xi. The B is the B, and the -1 is the -1. And now we can simplify. And when we simplify here, we have to look at how is the results for these different components. And what we see here when we do this step by step, I don't do this here, we have to multiply all these different possibilities with each other. Look that this is a vector here that is transposed, and then we do the dot product with this vector. And so we look at all the different components j and k that we have for our x's. And here we take this alpha I and yi and include this here. And these components are also included with the b, and they're also included with the -1. And we had the constraint before on the page that this term must be 0. This term, if you look at it, is the same term twice. Therefore, what is left is this term. This ends up here. And this is the same term twice, but here we have 1/2. So we have -1/2 this term. And this is now our loss function as it depends on our Lagrange multipliers alpha. And now we want that we have an alpha such that this loss is maximal. So look for all those alpha such that this loss, where we already have found a certain x representation depending on alpha, and we have this problem, and we have the requirements that the alphas must be positive or at least larger than 0 or equal 0, and we have this constraint. And this is the dual problem to our primal problem. So with this method of Lagrange optimization, we have now taken this optimization under one set of constraints to a new representation and a new set of constraints. And this is one which is solvable with quadratic programming. I don't elaborate here how this works. There are certain Karush-Kuhn Tucker conditions on alpha I, and there is an analytical solution for this. And in the end, it gives us, however, this function in the form alpha I, yi, xi, x. So I use my data instances plus b. And alpha I is only positive, so different from 0, if xi is a support vector, when I have done all this optimization. And of course, one can also do this with slack variables and also transform this to the Lagrangian, and this gives you some more Lagrangian multipliers also for the slack variables, which are then constrained to positive values. So here, this is the primal version of the classifier, and this is the dual version of the classifier. Now, what happens here? What is this term? This is a particular data point, and this is a data point that we want to classify. And what is the dot product between two data points? What does this give us? A kilo? I don't understand the word, I think. A vector is a kilo? A scalar. It gives us a scalar. Yeah, that's correct. And what does this scalar express? When I have two vectors and I do the dot product, I return a scalar. But what does this scalar express? Exactly. So, as you correctly say, the dot product between two vectors is relative to the angle between them, just the cosine. Of course, that is true if the vectors are normalized. They don't necessarily need to be normalized. But this also means that aside from the length of these vectors, whether they are similar or not is indicated by this dot product. So basically, when you provide a new object here, you check here how similar this object is with the support vector. That's what you basically do. And therefore, it says here, this works a little bit like a KNN classifier. Which object is closer to which kind of support vector? So, and here, just for remembering, this was the primal problem and this was the dual problem. And now, why is this interesting? Because it allows us to do kernel tricks. As I said, this is like a similarity. And now let's say we want to classify these red dots away from the blue dots. Then this dual representation does not really need the value of x. All that it needs is the similarity of x with the support vectors. So rather than working with the x itself, we just work with this similarity. We can, for example, take a feature function. Instead of x, we provide a feature function phi of x, just as we did with linear regression. And, well, then it's the same thing as before. And, well, like before, when we, for example, here, let's say here we have one dimension, we have this class of rectangles, but on the right there are triangles and on the left there are triangles. And in this one-dimensional case, I will not be able to indicate one hyperplane. What is a hyperplane on this one-dimensional line? A dot, exactly. A single dot is a hyperplane. In this case, one dot is not sufficient to separate the rectangles from the triangles, right? But when I map this one-dimensional line into two dimensions, with this, for example, with such a parabol, then I can introduce, so basically I keep the x values and I introduce an x squared valued, and my feature function is mapping x to x and the second dimension to x squared. Then I get a parabol, and now I can separate these rectangles linearly in this higher dimensional space. Or when I have such a problem, I can, instead of representing things with x1 and x2, represent with x1 square, x2 square, and some linear combination of x1 and x2. So I go from this two-dimensional space to this three-dimensional space. And in this three-dimensional space, I can find a hyperplane that separates the red dots from the blue triangles. So the data becomes linearly separable. And then I can solve it by a linear classifier like a support vector machine. And in a support vector machine where I have this. How can I do this? The problem is phi of x often maps to a high-dimensional space, r to the power d, where the capital D is much larger than our original space. If you remember with linear regression, we said, we can maybe take all the squares, but also all the linear interactions between attributes. Let's assume you have 100 attributes. And instead of a linear problem, you want to have a quadratic representation. That means not only would you have x1 square, x2 square, x100 square, but you would also need to include the linear interactions, x1 times x2, x1 times x100. So that would give you like an, out of 100 attributes, you make more than 10,000 attributes. So this d would be much, much larger than this lowercase d. But when you take the dual representation rather than xi transposed x, what you get is phi of xi transposed phi of x. And no matter what the function is, I mean, you might still compute it at this point. You could then solve this dual problem and find the optimal separating hyperplane. Now, actually, even we do not even need the phis. Why not? Because the phi of xi never happens in isolation. It only happens together with the phi of x. So rather than representing the phis, what we represent are kernels. A kernel between xj and xi that has the same value as this one. And what I said to you before when we used kernels for linear regression is what we can do is we can rather directly represent the similarity between support vectors and the vectors that we are interested in. And do not even go to the explicit representation of the phis, and then be able to also nicely learn circular boundaries just by defining the kernels. And people come up with many kernels. People even try to learn kernels. And so you then have such a kind of a kernel representation of support vector machines, which then looks like this. Instead of the phi of xi, phi of x, you have the kernel between xi and x. And this is then your dual problem, which looks only slightly differently than the original one, but can be solved with the same quadratic programming approach. So, example kernels. A linear kernel is the one that was our what we put in. A polynomial kernel. Yeah. So here you would 1 plus x transposed x prime. You add this and compute to the power of d for any d. And this contains all polynomial terms up to a degree already. I mean, that's quite cool. Yeah? I mean, if you would explain this in detail, you would have different terms for example, x to the power 3 or x to the power 2 times x prime and so on. All these are contained in here. The Gaussian kernels, we also called them radial basis functions before. This is always a very powerful one. It explains the difference, the similarity between x and x prime. If they are very similar, then this is 0. E to the power 0 is 1, so it's a high similarity. If x and x prime are very dissimilar, then the similarity goes against 0 very quickly. And the sigma square regulates how broad the similarity field is. There are kernels also for other structures that you cannot represent directly in a vector space. So when you look at graphs, when are two graphs similar, or when are two nodes in a graph similar? You can do random walks and then count how many nodes overlap in such a random graph. Right? Let's say you have a graph. Now, how similar is this node to this node? You can start random walks in this graph, and on these random walks, you note, for example, let me do this differently. Let's make this like this. On this random walk, you would, for example, say, this is I observe when I start here, and this I observe when I start here, and when I start here, I observe this and this. And you could count how many nodes overlap in this random walk. And you can turn this, for example, using Jacquard function, into a similarity assessment, and you can use the similarity assessment in your support vector machine. So you can even work with discrete structures that are not in a vector space. You can do this with strings, edit distances and stuff like that would otherwise not be possible. So you can build your own kernel for your own problem and use this with your support vector machine, even in spaces that are very hard to imagine. So as I think I said before, instead of inventing funny nonlinear features, we may directly invent funny kernels. That's what Marc Toussaint said. I like this so much that I quote it here. And inventing a kernel is intuitive because you just express how correlated how similar x and x prime are in terms of the correct function annotations or the correct label annotations. And this is also often much more intuitive than defining the features that work. And well, there's a whole literature about support vector machines, whole books. For example, Ingo Steinwart, a mathematician in the neighboring faculty, wrote a whole book about support vector machines. So, and Bernhard Schulkopf from Cyber Valley and Max Planck Institute, he invented several important techniques around support vector machines. For example, there is also a technique for one-class classification with support vector machines. So here we always describe support vector machine as a separation between different instances. There are also support vector machines where you just give one class and you try to find a nice closing of this one class, which is useful when you look at anomalies. So you observe a machine, how it's running, and you don't have an example for how it's running unnormally, but if it's running differently than what you know, it's a bit like maybe if you're a car driver or bicycle driver, that doesn't really matter. When something sounds funny with your bicycle, differently than otherwise than you're used to, you have the feeling there must be something wrong, right? So this is a one-class problem because you don't have full insights into how your bicycle could sound funny. And it's just funny and awkward if it's different than what you have experienced before. So this is a one-class problem, and such a thing you can also do with support vector machines. That's good enough for today. Next time we will close support vector machines with transductive classification, but let me explain next week what this is. Have a nice week in the meanwhile, and see you.